Hey, what's up, guys? Chung here again. And today let's take a look at another LeetCode problem here. Number 1293. Shortest path in the grid with obstacles elimination. You're given an m times n 2D grid where the cell could be either 0 or 1. 0 means you can pass, and 1 means it's obstacle. And you can move freely in 4 directions. And it asks you to return the minimum step to walk from the starting point to the ending point, basically the top left corner to the bottom right corner. But the only catch here is that once you reach like an obstacle, you have an option. You can you can try to remove this obstacle, but there's a limitation here. You only can remove at most k obstacles, right? And that's the limitations you have here. And with that, it asks you to find the shortest path. Right? So I think this is like pretty a strong hint, right? We should use a BFS search because so basically this problem has like all the characteristics we need for BFS search. We have a starting point, we have an end point, and it asks us to find the shortest path, right? That's obviously a BFS search. And the only thing we need to handle here is how can we handle this case here, right? Mm. So in the general normal BFS search, we will have a visited like we have a scene set, right? And this set basically will store all the visited nodes, right? And we don't revisit the same nodes over so that because if that's the case, we'll be ending up in an infinite loop, right? But in this case, one node could be visited more than one time, right? Why is that? Let's say we have this one. Mm, let's say we have this 0, 0, and 1, 0, right? So let's take the easiest example here. We start from here, right? And the first breadth first search will be either basically we'll be searching this, we'll be adding these two numbers, two nodes into our queue, right? And then from here onward, okay, so basically every time when we add like this queue here, so we have to check if the current state can remove this can be removing these obstacles, right? If the remaining k is greater than 0, then we know, okay, we can remove this one so that we can add these things. We can add this node to the to our queue. But from here onward, right? So, both this one and this one can both this one node and 0 node can both reach this 0 here, right? And if we only using the normal BFS search template, which let's say if we process this one first, and then if we mark this node to be visited, and then we have a better answer here, right? Basically, this answer is better than the one because the k here we are basically we reduced 1k here, but when we go this route, right, there's no need to reduce any k. Okay, so that's why we cannot simply mark this node as to be seen simply using the coordinates, right? So instead of I and j, we have to add the third state here, which is the k. So then it brings up to this like thought here, right? So when we do the BFS search, we have a scene here, right? what does this scene stores, right? At the beginning, we thought that the scene here only stores the coordinates of the node, right? Basically, when we do the set here, right, we only do a when we only save the I and j, right? But what's the essence of this scene here, right? Does it only say stores the coordinates I and j for the BFS search? So if you think more deeply, what it stores is actually the state of that node, right? And at the a normal BFS scenario, you by using the I and j can uniquely identify that state. That's why we use I and j to annotate the state of this position, right? Because for BFS search, there's no other factor. All we have is the coordinates I and j. So it's safe for only use the I and j to uniquely identify the state of this node. But in this case, since the state, because the state from coming from this 1 to 0 and from this 0 to 0 is different. Okay, so for the regular BFS search, if there's no k factor here, so the the state from the state traveling to this current node from the left and up are the same. That's why we can simply use the I and j to uniquely identify this current state. But in this case, again, traveling from the left and up to this same location here is different, right? Why is that? Because if we're traveling from top down, the k will still keep the same, right? But if we're traveling from the left to right, right, and then the k will be smaller, will be k minus 1 in this case, because if we go this route, the k by reaching the same location, the k will be different. So basically, and that's why in this problem, each node, the state can to uniquely identify the state of this node, we have to use I, j, and k. Right? Okay, as long as you can come up with this like state identifier, all the left is just the regular BFS template. That's all. Okay, so let's try to code this problem up. Okay. So m, right, n grade 0. Okay, right, and so we'll be having a queue, right? Queue for our BFS search collections DQ. Okay, and the first one 0, 0, and k, right? That's the first, and then we have a scene set, okay, and scene is at, right? So same thing here, 0, 0, and k, and then we have an answer here. Answer is starting from 0, and all it's left is just to write a normal BFS template here, while q, right? Then I'm using a for loop to keep counting the steps here. You can also add the steps to each of the state here, which will make this three-dimensional tuple into a four-dimensional tuple. Either way is fine. But for me, I just personally prefer using a for loop to keep track of the current steps. Okay. Q, right? So we have a I, J, and K. Okay. Pop left, right? And then in the end, we simply increase this by 1. So, and here we return the answer. And So basically every time we have I and j, we simply check if I equals to the n minus 1, right? Basically I check if the current node is the last one, then I know, okay, I have reached the target, right? If j equals to n minus 1, right? I simply return the answer here. Otherwise, right? Otherwise we just need to do a BFS, right? So, and to do that, we have to define like a directions here, right? Up, down, down, left, and right. Okay. So for directions in directions, and new I equals to I plus D0, right? So all this is just the regular normal BFS template, right? And then we do a range check, right? A boundary check. I M and J N, right? So here, yeah. So here, to check the rest conditions, we need to have like two separate cases. Why is that? Because uh, based on the new value, if it's a 0 or 1, we have to for 1 we need to decrease the k, right? And if it's 0, we keep the same. So basically for here we have two else here. If the grade new I and new j is 1. Okay, let's check the ones here. So if this thing is 1, right, and then basically we need to check if the k is greater than 0, right? So that means if we still have still have some k's left, then we can continue at this path. Otherwise, we should just stop here, right? And then if the k is greater than 0, and what? And I also need to check if that's the state has been seen before, right? And basically ni, because we always need to check in this case k minus 1, right? In scene, right? Since like I said, we will be having like a 4-dimensional state here, dimension state. So that's why we use this state. Okay. Okay. So if all the check pass, now we can simply add this thing to the queue, right? Append. Okay. And of course, now we need to also add this state, the state to the scene here, right? So the that's the one case. For the 0, right? For the 0, it's easier basically. For the 0, we don't need to check this. We don't need to check this k here. All we need to check is I'm gonna copy this here. All we need to check is if the new I, j, and k is in the scene here, right? Because we don't need to worry about the obstacle in this case. So we simply do a j, new I, new j, and k. Okay. Yeah. Cool. Yeah, I think that's pretty much it is for this problem. Let's see. I, j, and k answer. We increase the answer by 1. We do a four directions BFS search. Then we check the boundaries. Then here we have two conditions here. If k is greater than 0, and then we continue on this path, right? And if not, we just stop here. Okay, let's try to run it. Oh, range. Okay. What? Hmm. What did I do wrong here? I, J, and K. Maybe I shouldn't use K here. Maybe I should use current K just to be different, to be the original K here. Will this work? Okay. Hmm. Seems like that's not the case. Hmm. How about this one? 0, 1, 1, 1, 1. Okay, so this also looks fine. I think I know what did I do wrong here? And not, right? Not in, not. Okay. So we only add to the queue if this new state has not been seen before. Same thing for this one here, right? And then let's try to run it again. Not in. Yeah, okay. Let's try to run it. Minus. Oh, sorry. Uh, return -1. Okay, basically, if we never seen the target, the ending point, in the end we return the -1. Cool. Yeah. So it passed. All right. So just let's do a quick recap. So basically, from reading the description of the problem, I think it shouldn't be too hard to come up with the BFS approach. And the only things we need to be careful here is this is not a regular I and J BFS search, because we need to find a third factor to uniquely identify the current state. That's why we will be adding the K, basically the current remaining K for the current state, right? And other than that, it's just a regular BFS template, and uh, the the only small variations here. So with different values of the new coordinate, we do either will be basically generate two different states from here onward, right? And after that, yeah, nothing special. All right, cool guys. I think I'm gonna give it my own upvote. Yeah, thank you so much for watching this video, and I hope you can learn something from each of my videos. And stay tuned. See you guys soon. Bye bye.